Okay, so let us start. Today I'm going to talk about quotients by algebraic group actions. And the aim of this talk is not to present some concrete result, and even not to survey some results, but mainly to fix some terminology and basic concepts. Because several decades ago, when we had a regular seminar in Moscow State University, it was very usual for us to discuss quotients and all this business, and all of us knew basic definitions and so on. But time goes quickly, and it seems that new generation is not so familiar with this. And sometimes I see that people use words not in a correct sense. So I would like to discuss what is a quotient from the very beginning. Okay? So let us take some group G acting on a set X, and then we consider the quotient X mod G, just by definition, just the set of orbits. So one point in this set is an orbit for my action. Okay? And this set parameterizes the set of orbits because this is a set of orbits. Okay? And even it can be treated in a wider generality. We may assume that we don't have a group action, but we have some equivalence relation on our set. And equivalence classes are points of the quotient space. And there are quite many papers when such a general approach is considered, when you have some, say, algebraic variety, you have some equivalence relation, and can you construct another variety whose points are classes of this equivalence relation. But for us, this is too general, so our equivalence relation will be relation to be in one orbit. So we consider orbits, and we consider quotient as a set of orbits. But set theoretically, certainly this is interesting, but this is called combinatorics. This is not what we want to do. And we will consider, firstly, topology. If X is a topological space, then we may define topology on our quotient space, X mod G. This is called quotient topology or factor topology. And this is the weakest topology such that the quotient morphism is continuous. I forget to say what is a quotient morphism. Certainly we have a projection phi from our set X to this set of orbits, where each point goes to its orbit. And this is a point in the orbit space. Okay? And this is projection. Is everything clear what I said? So please interrupt me to ask questions because it should be completely clear. And if you know that there is some topology on X, then you can introduce canonical topology here. And this will be the weakest topology such that this morphism is continuous. This map is continuous. Namely,
topology.
Sorry?
This strongest topology.
I think weakest. This is the minimum number of open set.
We always have anti-discrete topologies.
Weak topology, this is when we have many or small number of opens.
Small number?
Okay, then I'm wrong. So I want to have a minimal number of open subset. Let me say that...
Maximum. You want to have maximum?
No. Okay, let me take the definition. We will see. Let's say that a subset in the quotient space is open if and only if its per image is open in X. So I should say that these subsets are open if I want my morphism to be continuous. And I don't want to have more open subsets. Okay? Now we can also define a sheaf of function. If my X was a space with a sheaf of functions, then we say that sheaf of function on X mod G, this is denoted by O, and this is just the direct image of the sheaf of invariant functions on X. So we say that functions on open subset V inside of the quotient space is precisely the invariant functions on pre-image. Okay. And also, so phi is continuous. This first observation. And second observation is that pre-image of some image of a subset M. So I take some M inside of my X. I firstly project it to the quotient and then take the pre-image of this projection. Then this is directly from definition, this is a union over all G and G of shifts of this subset M. Okay? And this elementary observation implies that projection is open. Let me recall that morphism is continuous if the preimage of open subset is open, and map is open if the image of an open subset is open. And this is straightforward from this. If this is open, then shifts are open and union is open. Okay. And also we can claim that image of a subset Y is closed. But this will be true not for any closed subset, but provided this Y inside of X is closed and G invariant.
So we assume implicitly that if X is a topological space, then the action
is continuous. Certainly I are working the corresponding topology. So if I assume that this is a topological space, then I assume that this is a topological group, and this is a continuous action of the topological group. So this is always presumed. So we can assume that the image of a closed subset is closed, but we should also ask that this closed subset is invariant. So certainly we will be interested in algebraic varieties, and very basic problem which appears from the very beginning is that even in reasonable and classical topology, this space can be non-separate. One point can be in the closure of another point. Why? Just because one orbit can be in the closure of another orbit. Secondly, this is very typical. You have some, I don't know, some open orbit and some orbits in the closure. And on the level of this quotient space, one point will be in the closure of another point. This is somehow bad, and people try to overcome this problem, and solutions very general. Solutions. Two variants. Either glue some orbits. If one orbit is in the closure of another orbit, then we will say that this is the same orbit in the closure. We will identify some points in the set of orbits and obtain some smaller but geometrically better quotient space. Or another variant is to take away some orbits. So to substitute our X by some open subset with a good orbits. And orbits outside will be bad, we will not consider them. And we will construct quotient space for this open subset of good orbits. And both these approaches will be considered today. So from now on, we assume that X is algebraic variety. Sometimes it is reducible, so I will not prove anything, so I will not take care about technical assumptions. And G is an algebraic group. And now I come to first important definition. If this X mod G is an algebraic variety, then this map, this projection, is called a geometric quotient. You can ask, what do I mean algebraic variety? This is just a set, and it's a philosophical question when set is an algebraic variety. But certainly I mean that this set with this topology, with this space of this sheaf of function, should be an algebraic variety, and this should be a morphism of algebraic varieties. So if this turns out to be the case, then we say that we have a geometric quotient. Also, the question of terminology: what is geometrical? What is geometric quotient? This space or this morphism? It's correct to say that this morphism is geometric quotient, but certainly people also call this space sometimes. But this is some approximation to good terminology that this is a geometric quotient. Okay, so let me observe that in this case, certainly we conclude that all orbits have the same dimension. If I have a geometric quotient, then all orbits of my action have the same dimension. I assume that X is irreducible. Why? Elementary exercise, because you know theorem about dimensions of the fiber. If you have a morphism, then you have some generic dimension of a fiber, and some specific fiber can have bigger dimension. Okay? An opposite situation with orbit. If you have an action of an algebraic group, then on an open subset, dimension of orbit is some fixed number, and in the complement, dimension of orbits can be only smaller. So dimension of orbits in specific case decrease, and dimension of fiber increase. So if orbits are fibers, and this is exactly the case for geometric quotients, when orbits are precisely the fiber sources, then we should have that all orbits and all fibers have the same dimension. But we will see soon, elementary example shows that this condition is necessary but not sufficient. You can produce actions such that all orbits will have the same dimension, but there will be no geometric quotient. The question whether geometric quotient exists is much more delicate. Again, elementary claim, which you can find in Popov-Weber book, tells you that if I have some morphism from X to Y, and I always assume that some algebraic group acts on my variety X, then it is a geometric quotient. If and only if I have four conditions. Condition number one, pi is surjective. Condition number two, pi is open. Condition number three is that fibers are precisely orbits. And condition number four is about functions, C form, that pullback map, which sends a regular function on some open subset V in the quotient space to functions on the pre-image. Such functions will be automatically invariant because my orbit, my map is constant on the orbits. So certainly any function downstairs, if I will pull back it upstairs, then it will be constant along the orbit. This is clear. But requirement, this condition number 4, is that this is an isomorphism. So any invariant function upstairs can be obtained as a pullback of some function downstairs for any open subset V in the quotient space Y. And even stronger claim, this may be considered as an exercise. For geometric quotients, this is easy that all this is fulfilled. And another direction, maybe a bit more difficult, but also true. Claims that if Y is normal, then geometric quotient is equivalent not to 4, but only to two conditions, namely C1 and C3. And C2 and C4 are fulfilled automatically. Okay, example of geometric quotient. If you have an arbitrary algebraic group, not necessarily affine, any algebraic group, and if you take a closed subgroup, then you have a morphism projection from G to the homogeneous space. Set theoretically, this is a set of left cosets, but this is basic theory of algebraic groups, that this set of left cosets, it always has a structure of algebraic variety. And orbits will be precisely these cosets. So this is a geometric quotient with respect to right H action. And this is an example of geometric quotient. Okay? So it was definition number 1, and I come to definition number 2, which is maybe even more important, as this is about categorical. This will be again a morphism pi from X to Y, where X and Y are algebraic varieties, and again some algebraic group X on my variety X, and it should satisfy the following universal property. For any morphism from X to Z, where Z is again algebraic variety, no G action, but this morphism should be constant along G orbits. There exists and unique morphism which makes this diagram commutative. So any morphism which is constant along the G orbit should be obtained as a composition of two maps which comes through this Y. Okay? It's very easy to prove several things directly from this definition. For example, it follows from this that pi is surjective. Why does it follow? Because if pi is not surjective, say if the image of pi is contained in Y without some point, if some point Y naught is not in the image, then you can consider new variety. This Y without this point. If you remove a point from a variety, you will obtain open subset, which is again an algebraic variety. And then you consider this morphism phi. This will be the same as pi, but from X to this new variety, with one point removed. And this will be again a morphism constant along the orbits. then you should have such a prolongation through y. And you can prove this exercise that there is no such. So in this case, this is more or less directly from definitions, this pi is subjective. Another point is that pi is unique. That if you have two morphisms with these universal properties, then they are isomorphic. You just apply this diagram this way and opposite way, and you obtain this uniqueness for categorical quotient. But the question of existence, where any action admits a categorical quotient, this is not trivial question. And the answer is no. I will give some example later that categorical quotient may not exist. This is not, and this is somehow bad news. Also, notation. You can denote, certainly when you write mathematical paper, you can denote everything as you like. But it's better to follow some general rules, because without this, it's very difficult to read mathematical papers and so on. So, usual notation for orbit space for quotient is like this. But this is reserved for geometric quotient. Here you assume that any point is one orbit, okay? And here this is not true. You may have quite complicated action, and the categorical quotient will be just one point. I hope that you already have some experience with this and you know such examples. And certainly you should use some another notation, so standard notation will be like this. 2 times. Okay?
So in what sense do you want quotients to exist? So they're always like schemes, but they're not always separated?
I will discuss this, but at the moment I consider all algebraic varieties. So I want to find a universal morphism from x to y, such that x and y are algebraic variety, such that any morphism in the category of algebraic variety admits such a diagram. So everything what I say is in the category of algebraic varieties. You can speak in the category of schemes, in the category of we will do it in algebraic space and so on. Okay. Again, this is like an exercise, that any geometric quotient is automatically categorical. But not vice versa. Okay, and now just to give you some feeling, I will formulate a theorem. I don't know how to prove it for the first time, but you can find it in Popov-Winberg survey text. Invariant theory, which I also hope that all of you regularly read. Before sleep, you take the Popov-Winberg book, read it, and then go to sleep. And the result is, but certainly it was known before this year. It says that if you have a finite group action, certainly the case of finite group should be somehow easy. People expect that for finite group we can understand it. And yes, we can. If it acts on an algebraic variety, then geometric quotient exists. And certainly we expect, for finite group, we expect only geometric quotient. It's difficult to imagine somehow that one orbit is in some sense in the closure of other orbit because it's finite group. So intuitively, you are first interested in geometric quotient. If and only if, for any G orbit, it is contained in an affine open subset. So necessary and sufficient condition for existence of a geometric quotient for a finite group action is that any orbit is some finite subset. Okay? It is contained in one open affine neighborhood. By definition of an algebraic variety, any point is contained in a affine open subset, because any algebraic variety is glued from affine Charles group, right? But we want any orbit to contain in one affine chart. Okay? You can find a proof in one direction. Here, in another direction, this is maybe a bit more difficult, and at the moment I cannot give precise reference, but you can try it by yourself. And already Data observed that this is not always the case. Namely, Data gave an example of group of order 2. When we speak English, we denote group of order 2, not as we usually do, but in this way. Okay? So this is a group of order 2, which acts on some variety x, and this condition is not fulfilled. This is quite exotic example. Let me explain why. Because our corollary of this theorem says that if x is quasi-projective, then geometric quotient exists and is quasi-projective again. This is quite clear. Just from this is from definition of quasi-projective variety. Quasi-projective, this is open in some project, and you can prove that for any quasi-projective variety, any finite subset, it doesn't matter whether it's orbit or not, any finite subset is contained in an open affine chart. Okay, this is elementary. Much more delicate statement. It even has a name, Kleiman criterion, maybe two names, Kleiman somebody else, two names, that the converse is true. If you have an algebraic variety such that any finite subset is contained in one open affine chart, then it is quasi-projective, or non-trivial state. And there is another theorem. We can consider so-called. Is it okay that if I don't try, I just tell you? I hope you understand. There is a statement that, let me say that variety has a two property if any 2 points are contained in the open affine chart. Okay? And there is a theorem proved by Dokladchik that algebraic variety has a two property if and only if this is embeddable in toric variety. And this is beautiful theorem. Because what does it mean quasi-projective? Quasi-projective means embeddable in projective space. Because quasi-projective, this is something open in something closed in projective space, right? And if we replace projective space by something else, and what can be else for projective space? Toric varieties, such a beautiful object, you know. Which varieties are embeddable in projective variety, in toric varieties? Surprise, not all. And very nice characterization. Variety is embeddable into toric variety if and only if any 2 points have common open affine neighborhood. Okay? But can we construct examples of varieties which don't have this property? Yes, we can. And this is, say, Data maybe was the one who constructed this. Because here our group consists of 2 elements. And here this quotient does not exist. If this variety will have A2 properties, then any orbit consisting of 2 elements will be in one open subset. So this is an example of a variety without A2 property. But Data example is more difficult, as there are simpler 3-dimensional, this I can understand easily. It comes from geometric invariant theory, example of variety without A2 property. But this or that we can construct even free. In Data example, this is a free action. Even a free action of a finite group of order 2, such that geometric quotient is not exist. Okay. And can we have quotients by finite group of something not only affine, but say of something projective. Yes, we can, as I recall. Maybe the main example is the projective setting. Example. Weighted projective space. You take projective space of dimension n, and you take n plus 1 weights. So say positive integer d naught, d1, and so on dn. What is this by definition? This is by definition usual projective space, and then a quotient with respect to a finite group action, namely we take a product of cyclic groups. So on. How does this product act on your projective space? You interpret any cyclic factor as a group of roots of unity, okay? And you multiply the corresponding homogeneous coordinates, z0, z1, and so on, by the corresponding root of unity. And the quotient with respect to this action is called the weighted projective space. It's not immediate why such a quotient exists, but you can construct this using approach construction. This is basic algebraic geometry. It's written in my textbook that such a quotient exists, and this is an example of quotient for finite groups. Okay, and so looking at this theorem, if we don't have quotient and we want to have, what to do? Our idea is to enlarge the category. So to go from algebraic varieties to some wider category. And people who like abstract things, they do it quite regularly. So they create new and new categories, and the question is whether these categories do live longer than the person who's an event. And for this purpose, people invented algebraic spaces. This is quite reasonable thing. This can be imagined geometrically. I will not give a formal definition. Algebraic variety is glued from open affine subset, and so we have two affine subset. We have some open subset here, and they are isomorphic, and we glue these two charts along the isomorphic common subset. And the idea here is that you can do this gluing, identifying up to étale covering. But to give a precise definition, this is not so easy. And in fact, this construction was introduced especially to have the theorem that a quotient by finite group exists. And this was successful. There is a book by Martin from the 70s, I think. It's called Algebraic Spaces. And this is some series of the spaces, both abstract and quite geometric, quite concrete. And the main theorem here was proved by Deli. And it says that if G finite group acts on some algebraic space, in particular on algebraic variety, because algebraic space is some generalization of algebraic variety, then there exists a geometric quotient, which is again an algebraic space. So if you will sometime interested in how to construct quotient for some difficult action, you can study this book by Upton and to learn about what is algebraic space. And also there is one more theorem you can claim that any normal algebraic space is obtained as a geometric quotient of some variety by some finite group. In this sense, algebraic spaces are precisely geometric quotient of varieties by finite group actions. So, if such a quotient does not exist, then we just say that it should exist, but it's not algebraic variety, but we assert this is algebraic space. So something like this. And also there are many other generalizations. Say there is a concept of stacks. This is the most popular construction which guarantees that quotient exists in very general situations, but this is non-geometric. This is completely categorical concept, and this is difficult to understand. But now, if you want to see other publications on invariant theory in top journals and annals of mathematics, yes, there are. They are something like lunar slice theorem for stacks. This is a recent paper in annals of mathematics. So this is a very popular object. And also you can consider non-separated spaces, algebraic variety, which are not algebraic variety, which do not satisfy Hausdorff axiom. They are called pre-variety, non-separated. You may consider constructible sets, and so on. Many extension of the category of algebraic varieties which allow you to construct this or that quotient. And historically, many categories were introduced just because people wanted to have some quotient. But stacks are the most actual and popular. Okay, but after this general introduction, I go to part 2, and I want to give you 3 constructions. I start with construction 1. This is about rational geometric quotient. This is very old, very useful classical theorem by Rosenlicht. Tells you that if some algebraic group, not necessarily affine, any, acts on some irreducible algebraic variety, then there exists a finite collection of rational invariants okay, not necessarily regular, because you might have a projective varieties, there are no non-constant regular functions. There are rational invariant and an open subset firstly that these functions are regular in this open subset, but this you can achieve by shrinking your open subset. Okay? And what is important is that 2 points x, y, and x2 in this open subset are in one G orbit if and only if the values of these functions at this point coincide. Okay? So 2 points are in the same G orbit if and only if the function f1 has the same value at these 2 points, and so on. The function fr has the same value as this point. So, usual term that this rational invariant separate generic orbits on your gravity. So there is a finite collection of rational invariants such that they separate orbits in some open subset. Okay? And from this, there is a very nice conceptual proof in the book by Popov. So if you didn't study this, but I think that you passed through some basic courses in invariance here, so maybe you already know this proof. But if not, then please look into the book. And corollary. Which after some work can be concluded from the theorem, that there is an open subset W, open and G invariant, such that there exists a geometric quotient. So, conclusion of the Rosenlicht theorem that a geometric quotient always exists for any group action or any variety. But you should substitute your variety by an appropriate open subset. Okay, and now this is also quite active research area. People do some generalizations. But what can be more general? Any algebraic group, not necessarily affine. Any reducible variety, not necessarily projective or affine. What can be generalizations? Take infinite dimension. So we started with when G is algebraically generated. This is in our paper by 4 authors with Flanner, Kaliman, Kuchebau, and Seidenberg. And algebraically generated means that you have an action of many algebraic groups of your variety. And you have to consider an abstract subgroup generated by some collections of algebraic groups. This may be infinite dimensional subgroup of the automorphism group, and then we also have the same conclusion. And then later Popov generalized it for any connected subgroup in the automorphism group. In the automorphism group you have some topology, this is in group, and you can say which subgroups are connected, and if it is connected, then Rosenlicht theorem. And even more, this is incredible generality, but even more general version is available, namely for some subgroups in the group of birational automorphisms, or some subgroups. So you may not have a regular action, but you may have a rational action, given not a polynomial by fractions. This is not a usual action, this is not an action in group theoretical sense. But this is a birational action, and it was proved recently in the paper by Data, Urich, and Van Santen. This is published this year in Inventiones. And one of the results of this paper is that there is Rosenlicht theorem holds true for birational. So people still study this. But this is not the main point which I wanted to say. I want to tell you another story. Construction. Device, just press one button and boom, it becomes clear. Such physical training. Okay, construction 2, maybe the most important one for us. This is about reductive group. And affine varieties. So I go directly to the statement because I think that all of you know this from your childhood. So if you have a reductive group, you know from each other. So it is a reductive group, so I don't recall it. And if such a group acts on a affine variety, then the claim is that there exists a categorical quotient, not geometric but categorical. Namely, this will be a morphism from X to the quotient space, which is a spectrum of the algebra of invariance, right? And this morphism is given by inclusion of the algebra of invariance into the algebra of regular functions. So, if you have an affine variety, then you have an algebra of regular function. This is finitely generated algebra, okay? And then we have a Hilbert theorem which tells you that the algebra of invariance of a reductive group is always finitely generated. So, there is some algebraic variety corresponding to this finitely generated algebra. This is called the spectrum of this algebra. And this is precisely the quotient space. And any morphism of algebras corresponds to some morphism of variety, so we should consider morphism of variety given by this inclusion. Okay? Naively, what does it mean? You take a point, and you send this point to a collection of values of generators of the algebra of invariance at this point. Okay? So x goes to f1 of x, and so on fm of x, where the algebra of invariance is generated by f1. Okay? How to prove that this is a categorical quotient? This is also given in Popov-Wilbur. This is basic exercise. This is really for exam. I don't know whether Timashov ask you this exercise when you pass your exam on invariance theory. This is really straightforward. Just take a definition and do this exercise that this is a categorical quotient. But from this very basic result, there is some corollary which tells you that the quotient space is affine. And this is not obvious at all. This is some miracle. And also I would like to stress on this result because we will go further to different generalization, versions and so on. And it will be some zoom of some strange examples, counterexamples and so on. And this too much destroys this theory. But such a hurt result is really the most important. Elementary, basic, many applications, so clear and so on. Because of this result, the theory makes sense. Certainly, also I would like to say that this quotient is geometric. If and only if all G orbits have the same direction. So for reductive group action on affine variety, the condition that all orbits have the same dimension is both sufficient and necessary for existence of geometry. Okay, and certainly you may find many properties. I will not list all of them. Say, for example, if it is a categorical quotient, then this morphism is surjective. And this is not clear at all. If you take some algebra, if you take some subalgebra, then this inclusion of algebra inside subalgebra always gives you dominant map of corresponding variety. But it need not be surjective. And the fact that this is surjective, this is also some miracle. In this case, this is surjective. Another important property is that any fiber of pi contains a unique on the one hand, certainly any fiber this is closed G-invariant subset, so it contains an orbit of minimal dimension, so it contains some closed orbit. But there cannot be two closed orbit in one fiber. Such a quotient map separate closed orbit. So this categorical quotient in this concrete situation, this space you might interpret points as closed G orbits. Okay. And many other properties which I'm not going to list. Let me give one example. Again, let me assume that G is affine algebraic group. No, not linear, but affine algebraic. And H inside of G is closed reductive. You have a reductive subgroup. Then the homogeneous space G mod H is affine. This is for free. It follows as a corollary from this result. Because you have a affine algebraic variety, you have a reductive group action by right multiplication. All orbits have the same dimensions, they are cosets, so you have a geometric quotient which is a affine variety. But try to prove it directly, this is quite difficult. And in fact, you know this is called the Matsushima criterion, that if G itself is reductive, then G mod H is affine if and only if H is reductive. But other direction, that if variety is affine, then H is reductive, is difficult here. And this way, this is for. And for arbitrary affine algebraic group, the question for which closed subgroup such a homogeneous space is affine variety is still open. Even no conjecture, no ideas. It's not known. There were several conjectures, but all of them were disproved.
So there are examples of non-reductive subgroups such that the quotient is...
Sure. But there are examples of non-reductive subgroup such that the quotient is affine, but for non-reductive G. Say if you take a unipotent group, even solvable group, then any factor group of any homogeneous space of solvable group is affine. And any algebraic group is a semi-direct product of reductive and unipotent. So the question seems to be trivial reduction to the case of reductive case and unipotent case. All reductive case and unipotent case are done. And this mixed case still open. Okay. Now generalizations. Can be weaker some condition. Weaker than G is reductive, or weaker than G is affine. There are many papers on this, and I also participated in this, but results are very poor. Say if you will try to weaken the condition that H is... Okay, let me first assume that G is not necessarily reductive. If G is not reductive, then you may have two difficulties. Difficulty number one is that this algebra can be not finitely generated. Firstly, it was a counterexample to Hilbert's Fuzzy problem when Data constructed unipotent group, commutative unipotent group, which linear act on some high-dimensional vector space, such that the algebra of invariance is not finitely generated. And then Popov proved that for any non-reductive group, you can construct appropriate affine variety such that the algebra of invariance is not finitely generated. So there are many cases when this algebra is not finitely generated. And then you cannot take this spectrum, you don't have this variety, and you don't have a candidate to go here. But people try to overcome this. If your algebra is not finitely generated, certainly it's not an algebra of regular function on some affine variety, but maybe this is algebra of some functions on quasi-affine variety. And your Klinkelmann proves that yes, this is the case. Any algebra of invariant is an algebra of regular functions on some quasi-affine variety. And this quasi-affine variety is a natural candidate for the corresponding quotient. But again, there are some difficulties in no general theorem that such a space is always quotient. Another difficulty is that even if it is finitely generated, then this map from X to the spectrum can be not surjective. You can easily construct such examples. For one-dimensional unipotent group, it's natural linear action. Say one-dimensional unipotent group acting on C2 plus C2. You can compute the algebra of invariance, and you will see that this morphism will be dominant, but not surjective. And so this is not a categorical. Okay, and what is the image of this morphism? Is it always old? No, it can be rather bad. What does it mean bad? We know that any morphism of algebraic variety has a constructible set as an image. So maybe we should go to the category of constructible sets, and this will be a quotient. Yes, we even wrote a paper on this quotient for category of constructible set, but this is not so. Sometimes we can guarantee that this morphism to a categorical space, to a constructible space, is a categorical quotient, is a category of constructible spaces. Again, no such a general result. I have one general result which I like, and I will mention here. This we wrote with Arzhantsev and Rosenlicht in 13. This is G is unipotent. It acts on some vector space, and the action is linear. Under this setting, we claim that there exists a categorical quotient if and only if, in the category of algebraic varieties, if and only if this algebra is finitely generated, and this morphism from V to the spectrum is surjective. And this morphism is a categorical quotient. So even if this algebra is not finitely generated, we may find a quasi-affine variety which has this algebra of invariance as algebra of regular functions, but this morphism will not be categorical quotient. It does not exist. Or if you don't have this condition. But this is for very specific situation, only for unipotent group and for linear functions. Okay, so maybe we should stop with this, because this is again big zoo of examples and counterexamples and no general theory. Let us try to weaken the conditions that X is affine. Let me give you two examples. Let me take X to be the simplest possible quasi-affine variety. You know that quasi-affine but not affine, the simplest case is to remove the origin from the affine plane. And what is the simplest reductive group? One-dimensional torus, right? So I consider one-dimensional torus, which consider here, which acts here, just by scalar multiplication. So the picture is like this. You have 0, but you remove 0, and all orbits have this 0 in its closure. Okay? So in this case, we certainly have geometric quotient. What will be the geometric quotient? Projective line, right? Who studied the definition of the projective space? This is precisely the definition of the projective space. But this is a non-trivial statement that projective space exists as an algebraic variety. So in this case, there is this geometric quotient. This is a projective line. So we see that even we move a little bit from the affine variety to quasi-affine. Quasi-affine, this is almost the same as affine. But here, categorical quotient is always affine. And here, this is completely different. Another example. Let us change a little. Settings are the same, X is again A2 minus point. Action for one-dimensional torus. Action is again diagonal, but we will multiply by tx and t minus 1y. Okay? The picture is the same again. You remove the origin and you have two axes. Say with y you go to 0 and with x and with y you go opposite direction, and you have some hyperbola at generic orbits. Do we have a geometric quotient? Sorry?
Yeah.
Which one?
Some singulars.
No.
We have.
Sorry?
Oh, it should be a curve.
It should be a curve, right? Because you have a two-dimensional variety and one-dimensional group action. Okay, the statement is that the geometric quotient exists, but this is pre-variety. This is a fine line, but with a double point. Why? How to prove it? Just consider an affine covering of a variety. Remove this axis, you will obtain a affine variety. And the quotient space for your action will be a fine line. And remove this axis. You will obtain another open affine subset. You will obtain again a fine line as quotient space. And then you should glue these two affine lines. And if in the case of projective line, you glue two affine lines in this way, then in this case you will glue this affine line identically. But these two axes will correspond to different orbit and they will not glue it. They will be this double point in the quotient space. So this is a somehow justification why people may consider non-separated variety. Not just because we have nothing to do and consider some strange definition, but because they really appears as geometric quotient for torus action. They really reflect the structure of orbits here. Do you have here geometric quotient in the category of algebraic varieties? No. Do we have here categorical quotient in the category of algebraic variety? Yes. Because this affine line will be a categorical quotient in the category of affine variety when you glue this point together. But this will not separate these two orbits. Okay? And I will not write it, but this is a very basic observation. If you have some algebraic variety, any algebraic variety, and if you have a free torus action on this variety, then there always exists a geometric quotient, but this quotient may be non-separate. Why? I assume that the variety is normal. Because if you have a torus action on a normal variety, it always admits an open affine t-invariant covering. This is called Sumihira's theorem. For any t action, your variety can be covered by open affine subset which are invariant with respect to the torus. Then you take, via this construction, quotients on this open affine subset by your torus action. You will obtain geometric quotient on your affine charts. And then you will always can glue this together. Just identify any two different charts along their intersection. You always can do this. But you will, what you will obtain may be either separated or not separated. It depends on the action. And this non-separatedness reflects the geometric property of your action. Okay? Okay. But I think that all of us like toric variety, toric geometry, and so on. So now we come to a very natural problem. Do I still have some time? Yes. Do you understand me in English? Yes. Amelia, do you understand me in English? Because this is a Russian language.
I already understand you in English.
Okay. This is Russian English. It's a different language. But big torus which acts on your toric variety with an open orbit, right? By definition of a toric variety, you have a torus which acts with an open orbit. To ask about the quotient for this section, not interesting because the quotient will be 1 point. Because if when you have an open orbit, all other orbits are contained in this closure, and any morphism constant along orbit will be a morphism to a point. Categorical quotient exists, and this is 1 orbit. But let us take a subtorus. And we might ask when there exists a categorical quotient. You have a toric variety, subtorus, and you ask when do you have a categorical quotient for this section. The question is purely combinatorial, right? So your toric variety is given by some fan, your subtorus is given by sublattice in the lattice of one parameter subgroup. And looking at this combinatorial data, you should have some good combinatorial answer. When the categorical quotient exists. Say, always exists in some sense. This is an open problem. Not known. Jürgenhausen invested several years in thinking about this. He published several papers about this. And he constructed many examples, namely categorical quotients. You may ask about varieties, and you may ask about pre-varieties. When you allow non-separated quotient, or you consider only algebraic varieties, only separated quotient. And he proved that all variants are possible. Plus, minus, plus, minus. What do I mean? There are examples when the categorical quotient exists as a variety, but does not exist as a pre-variety. So your variety is not a categorical quotient in the category of pre-varieties. And vice versa, there can be that a quotient exists as pre-variety, but that does not exist as a variety. It can happen that it does not exist here and does not exist here. Even more tricky thing, it can exist here, it can exist here, but can be different. So all possible variants are known, but if you're not interested in pre-variety, you can forget about pre-variety. Just you might ask, when it exists as a variety? Not known. Examples when it doesn't exist as a variety, I wrote it, but maybe I will not spend time to write it down. This is something like this for elementary actions. And quite elementary proof that for such elementary actions there is no categorical quotient. But this somehow theory in itself. So people do some intellectual games, and unfortunately no general theory. Okay, and I should go to the end, but one more very important definition. Good quotient. This is what all of you should know. You should know what is geometric quotient, you should know what is categorical quotient, and you should know what is a good quotient. This is 3 basic concepts. This concept was introduced by Sheshadri, Indian mathematician. And at the first glance, the idea to call it good quotient looks bad. If you know people who solve mathematical problems, they don't have time, they have only 4 hours to solve many problems in mathematical Olympiads, as they don't invest a lot of efforts into terminology. Say, this is good, this is bad, this is good, this is bad. In mathematics, this is not. But, how to say, this was invented maybe in the 70s, so this concept is as old as I, so very old. And during this time, it turns out that this is really good quotient. So this term turns out to be good. Okay, what is the definition? Assume that my group is a reductive. This works only for reductive group. And assume that it acts on some variety, not necessarily affine. Then again, good quotient is a quotient. So this is a morphism phi from X to some quotient space Y, which satisfy 2 properties. Firstly, phi is affine, G invariant. This is already two conditions, but let me say. Let me recall you what is an affine morphism. Definition is given in Harshorn book, but it means that for any open affine subset here, its preimage is again open affine subset here. Preimages of open is automatically open, but preimages of affine is quite rarely affine. And this is very strong condition. The preimage of affine open subset is affine open subset. Okay? What do I mean by G invariant? I mean that this is constant along G orbitals. And each orbit goes to a point. And second, this is that my map on the level of functions. I go to sheaf of regular functions on Y, and it maps to direct image of the sheaf of invariant functions, and that should be isomorphism. So, crucial point is affine morphism, which is constant along the orbit, such that invariant functions upstairs are precisely preimages of invariant function downstairs. But if you will work with this notion, you will see that this is equivalent to the following. That variety X is covered by open affine G-invariant subsets. Not any G actually needs open invariant affine covering, but in this case it should be. This is a serious restriction. And the quotient space is the gluing, let me write down in the same way, U1 over G union is U1 over G. So, what is the idea? There is a covering by open affine subset. For each this open affine subset, you constructed the categorical quotients this way, and then you just glue them together into a quotient space. If it exists, this is called G. This is called good quotient. Okay. Say if you studied in toric geometry Cox construction, I will not now discuss it in detail, but I briefly recall that there is a total coordinate space. This is a spectrum of Cox ring. Inside of the spectrum of the Cox ring, you have an open subset, big open subset, which is a relative spectrum of the Cox sheaf, and then your variety X is obtained as a quotient by Euron-Sever inquisitors, and this quotient will be good quotient. It follows from construction. So Cox construction is an example of good quotient in this sense. And now I come to the end, and my last part is construction number 3.
So good quotient is categorical.
Right, this is a good point. Good quotient is automatically categorical. This is our exercise. Is it possible to construct categorical quotient which is not good quotient? Yes, it's possible, but it's better not to do this, because this is a bad quotient. All good quotients are good quotients. So, part 4, corresponding to construction number 3. This is about GIT. GIT, this is geometric invariant theory. And we should understand these words correctly. This was introduced by Mumford in 65. Mumford, I looked, he was born in 37, the same year as Weinberg was born. And in fact, I always look at people who was born around my year of birth. But this is really impressive how many big mathematicians were born in 37 or 38. So you can look, many, whom you know very well, who are classical mathematicians, they were born around this year. Mumford is still alive and active. He stopped to do mathematics some time ago, and he turned to some computer vision, computer science. But he's one of the greatest mathematicians. And at this time, he was rather young, and he wrote a book. This geometric invariant theory was a book. And this, I also heard, do you know what does it mean in English, such a word? Because I didn't know. I looked at the dictionary, you know what does it mean? Я все сегодня в словаре, это означает мерзавец. So I just translated this word into Russian. So it has some negative meaning. And so people usually think the geometric invariant theory, this is about geometric methods in invariant theory. No, this is not about geometric interpretation, geometric construction. In fact, Hans-Peter Kraft wrote a book, Geometric Methods in Invariant Theory, just to show that this is not the same as GIT. GIT, by Mumford, this is one concrete construction. And now I will briefly explain this concrete construction. So we will start from the simplest case. We will consider reductive group acting on vector space linearly. So you consider just a linear representation of some SLN, SPN, anything, some reductive group. Okay? Then how to construct categorical quotient for this we know. This is just spectrum of the algebra of invariance. This is a fine case. But many people are interested in projective varieties. So let us consider the corresponding projective action. Then G acts on the projectivization. Do you have categorical quotients here? Yes, you have. What will be the categorical quotient point? If your group is not, if your group is connected and has positive dimension, I claim that the categorical quotient exists in this one point. Just because there are no morphisms from affine space, from projective space. From projective space, you can map only to, you have inverting set, but some projection with positive dimensions of fibers, no such morphisms. So no candidates. If there are no morphisms, then there are no quotients. So to make a quotient for the action of your G on the whole projective space, this is not interesting at all. But certainly people wanted to construct quotient because what is the aim of invariant theory among maybe the first aim? To consider object up to isomorphism. You ask how many elliptic curves do you have? You ask how many algebras do you have? You always consider elliptic curves or algebras up to isomorphism. What is isomorphism plus? This is usually orbit of automorphism group. So you're interested in a quotient because you want to parameterize orbits, to parameterize isomorphic classes. And this was the question which Mumford started from the beginning, to construct moduli spaces or quotient for certain orbits. So his idea was not to consider the whole affine space. He introduced the concept of semistable points, SS, like this. What is this? This is a set of points in projective space such that there exists a homogeneous function, f, which is a regular function on your vector space, which is invariant and homogeneous of positive degree, non So what is K of E? This is an algebra of polynomial, right? Algebra of regular function in a vector space. It has a natural gradient by degree. Polynomials of degree 1, linear polynomial of degree 2. This is a natural Z gradient, positive gradient, right? 0 degree are only constant, so we consider positive degree. And consider some invariant. So we assume that there exists an invariant, which is homogeneous positive degree, such that it doesn't vanish at the corresponding point. What is V? V is a vector whose line is our x. Okay? So that there should be non-constant homogeneous invariant which is non-zero on this line. Okay? And what is a complement? The complement is some closed subset. You can check that this subset is open. And this is a projectivization of so-called null cone. Also very classical object in invariant theory. You can consider vectors where all homogeneous invariants are zero. This is called null cone. By Hilbert Mumford criterion, point is in the null cone if and only if there exists a one-dimensional subtorus in your group G, such that the orbit of this subtorus goes to zero. So null cone is precisely the set of points such that by some one parameter subgroup in your group G, multiplicative one parameter subgroup, it can be sent to zero. Okay. And what is the Mumford construction? What is GIT? GIT is the following. There exists a quotient from this set of semistable points to the quotient space. This will be a good quotient. And this quotient is nothing but the quotient space is a union over all such function f, homogeneous or positive degree invariants. I take the principal open subset where this function is non-zero. This is open subset in my projective space. I want to be in my projective space. This will be affine open subspace in my projective space. I take non-zeros of some homogeneous polynomial. And since this is invariant, I can take a quotient by the action of G. Affine quotient by reductive group, this we know. This is a spectrum of the algebra of varieties. And Mumford checked that this quotient glue together to some funny variety, and this variety turns out to be projective. And this even can be interpreted as proj of this graded algebra of invariants. This algebra inherits a natural gradient by polynomial degree. And this quotient space turns out to be its proj. So in this case, the quotient space is a projective variety. And Mumford even was interested in geometric quotient, but to, oh, I should stop it, I will stop right now. Stable points, not semi-stable, but stable. These are semistable points such that there are orbits in the set of semistable points are closed, and the stabilizer is finite. And it turns out that if we restrict our quotient morphism to the set of stable points, then this will be a geometric. But this will be no longer projective, because this will be some open subset here. But this is somehow open subset which really parameterize orbits. The set of stable points may be empty, because there may be no points with finite stabilizers. But if they are, then they form an open subset, And we can guarantee that there exists a geometric solution. And there are many, many examples of about curves, about this and that, where Mumford, using this construction, prove existence of modular spaces of these quotient spaces. So it turns out to be extremely useful. And now I have -2 minutes just to say general case, because this is somehow naive construction. And Mumford wrote everything on the language of schemes. But after this book was rewritten together with Fogarty and then reauthored together with Kerman, and it became more written. But very briefly, I will mention the general case. Namely, I consider reductive group acting not necessarily on a projective space, but on some projective variety. And then I consider G-linearized line bond. Yulia gave us a talk about generalization of line bundles on September 3. And this is a basic ingredient in Mumford theory. You should have a line bundle such that Gx exists. And this should be M. And then the set of semistable points is defined as such points in X that there exists a positive K and a function which is G invariant of positive degree, but in this case it is interpreted as a regular section of the case tensor power of my ample line bundle, and then I take G invariant, such that this section is not 0 in X. And then again we have a good quotient. And again we can the same way define stable points and geometric quotient and so on. And this is a projective variety. And then it was a big theory about variation of GAT quotient. Because this construction, it depends on this L, and if I will change L, how much does it change the quotient space? And it turns out that one can guarantee that they are birational, but it appears some birational transformation among quotient spaces. When I change this line bundle, then I go from one quotient space to another quotient space, but they can be controlled how they change. And it was a big surprise that objects which are very important in birational geometry, called flip and flop, birational transformation from the Morris theory, Opana, they appear in this construction very naturally. And it was a big achievement, 2 papers by Dolgachev-Hu and by Tadeusz, called Variation in Geometric Invariant Theory, and it was very popular. But now, it's not forget it, some people continue to do this. Another question was, is this construction universal? If you have a good quotient with a projective quotient space, does it always come from Mumford construction? And then it was a big activity by Grevitsky-Virula and Orson Polish school, and they proved that sometimes yes, sometimes no, so there were many results about this. Can we obtain all quotient via this construction? So this is more or less all what I wanted to say. But I wanted at the end, certainly I don't explain this construction in detail. Some years ago we studied it in our seminar with all computations, examples, and so on. So if you will have some motivation to do this, we can do this again. But now I'm not sure that we are motivated. So I want you just to say all these words, connections, just when you speak about quotients, that you use it in the correct way. And Grevitsky-Virula wrote a survey called something like quotient by algebraic group by actions, something like this. Quotient by actions of groups. And very good, where he collected many results. Maybe this is 15 years old. Milinski passed away some years ago. He was Polish academician, and he was very interesting. I had the pleasure to meet him many times. I was in Warsaw. And very intelligent people from Soviet time, because he came to Poland from America, but he was in some sense American Soviet mathematician. And this is an excellent text, but this is very non-trivial in the following sense. It has a short introduction where he says that I will explain quotients of this construction, Mumford theorem, and so on. And then at the end, it has a short section which is called final remarks. And in this final remarks, this is completely negative. He says that, I'm sorry, the theory doesn't work. So let me read you the very last paragraph of this final remarks. As is I just quote. As a result, theory of quotient by actions of group as a whole at the present time does not appear as a uniform theory with well-defined language, methods, and aims, but rather a conglomeration of various examples and theorems that do not fit together as pieces from different puzzles and do not form one picture. So at the end of his survey, he said, I'm sorry. But this is very honest about this theory, because this is really, there is some core result about reductive group action on affine variety, some beautiful Mumford construction and many things about this, but around this only counterexamples and so on. So this is interesting, makes sense, but no general theory which can be applied by mathematical community in general, not only those people who study algebraic code. Okay, so thank you for your attention.